A Git commit hash feels almost too small for what it represents. You paste one object ID, and Git can recover a whole project snapshot, files, folders, and history context. The important trick is that the commit is not trying to contain all of that data directly. It is the visible tip of a graph. The commit object points at a top-level tree. That tree points at other trees and blobs. Each object is named by an ID derived from its contents, so changing the contents changes the name. Once you see the commit hash as the tip of a content-addressed graph, the magic starts looking mechanical. Start at the smallest useful unit, file content. In Git, the bytes of a file become a blob object. A blob does not care what the file was called in your working tree. It cares about the content. If two files have the same bytes, they can point to the same blob identity. If one byte changes, the content is different, so the object ID changes. This is content addressing. The name is tied to what the object is, not where you happen to store it. That gives Git a stable way to talk about data before it talks about file names, folders, branches, or commits. A repository is not only file bytes. It also has structure, names, folders, executable bits, and links from directories to children. Git stores that structure in tree objects. A tree entry says roughly, here is the mode, here is the object type, here is the file name, and here is the child object ID. That child can be a blob, or it can be another tree. This is where the Merkle idea starts to appear. Even before we name it, Git is not just hashing data, it is hashing references to named children. The directory becomes an object whose identity depends on the identities underneath it. Now imagine editing one source file. The edited bytes produce a new blob ID. The tree entry that points at that blob has to change, because it now contains a different child ID. If that tree is inside another tree, the parent tree changes too. The ripple moves upward through the objects that reference the changed content. That upward ripple is the core Merkle move. A parent hash depends on its children, so a changed child changes the path above it. But unrelated blobs and unrelated subtrees can stay exactly where they are. A small edit creates a new path of changed objects, leading up to a new top-level snapshot. The commit is the object people usually see, but it is not the same thing as the project tree. A commit points to the top-level tree for the snapshot, and it also points to parent commit or commits. It carries author and committer metadata, timestamps, and the commit message. That means the commit ID commits to more than file contents. It commits to a snapshot plus history context. So the careful mental model is this. The top-level tree is closest to the root of the project snapshot, while the commit wraps that tree with history. Git is not a textbook binary Merkle tree. It is better described as a content-addressed Merkle DAG. Now we can name the cleaner textbook data structure. Git is graph-shaped, so it is better called a Merkle DAG. A classic Merkle tree is a simplified version beside it. Leaves are hashes of the actual data chunks, parent nodes are hashes of their child hashes, and one compact value at the top is the Merkle root. Change one leaf and the hashes on its path to the root change. That root is useful because it commits to the whole tree. A Merkle proof uses the same structure in reverse. To verify one leaf, you keep the target data, the sibling hashes along the path, and the direction or order of each step. Recompute upward. If you reach the published root, that leaf is consistent with that tree. Once the Merkle tree structure is clear, other systems become easier to recognize. A Bitcoin-style block does not put every transaction into the block header. It puts a Merkle root there, and a proof path can connect a transaction back to that root. Certificate transparency logs use a related idea. The log publishes and signs tree heads or checkpoints, and clients can ask for inclusion evidence. Git taught us the content-addressed graph intuition. These systems make the proof workflow more explicit. The names change: commit, tree, block header, sign checkpoint. But the move is familiar now: compact root at the top, small path back to a piece of data. There is one caveat you should keep separate from the data structure. A proof only proves consistency with a particular root. It does not prove that the root is honest, current, unique, or the one you should trust. If an attacker chooses a fake route and a fake tree, they can make a local proof that matches their fake route. The system around the tree has to answer the trust question. In Git, that might be the ref, remote tag signature, or review process you trust. In blockchains, it is the header chain and consensus rules. In transparency logs, it is signed checkpoints, monitoring, and append-only auditing. So the reusable model is this. A Merkle tree makes a large collection of data behave like one compact commitment. Leaves represent the data, parent hashes summarize children, the root summarizes the whole structure. A proof reveals only the target and the sibling hashes needed to rebuild the path. Then comes the separate trust question. Who says this route is the right one? Git gives you the intuition through blobs, trees, and commits. Blocks and public logs show the same route plus proof move more explicitly. That is why the idea keeps showing up. It makes large state portable. If this made Git click, subscribe for more visual engineering explainers. For